Okay, section 2.2, Algorithmic Efficiency. I'm Piccone, Garbinian Divine, helped me write this book. Real-time computing for mechanical engineers. Check it out at the MIT Press website or the rtcbook.org companion site. Algorithms. An algorithm is a finite sequence of instructions used to perform a computation. Very broad definition. An algorithm usually solves some computational problem. For us, this computational problem usually has something to do with the user interface, measurement, or feedback control because of the type of system that we're designing. In the first few lab exercises, each of the functions that we write for user interface is an instance of an algorithm. An algorithm is correct and solves a problem if, for every valid input, it yields the correct output in some finite number of steps. However, for general computing, and even more so for real-time computing, many correct algorithms will not satisfy the time constraint requirements when instantiated. Algorithmic efficiency. An algorithm must be correct, and it must be efficient enough to satisfy time constraints. When applied to the same problem, the efficiency of two algorithms can vary widely. To complicate matters, the same two algorithms applied to a different problem can perform differently, and sometimes can reverse their order of efficiency. This means that the designer needs methods of analyzing algorithms and computational problems to determine which is best for a given problem. There are many ways of classifying computational problems and algorithms to solve them. For instance, it is very common to need to sort a list by some quantification of its elements, for example, magnitude or position in an alphabet. This is a sorting problem, and there are many sorting algorithms designed to solve such problems. If you can cast a computational problem as a sorting problem, you will find a large class of algorithms already worked out and evaluated in terms of efficiency for different classes of sorting problems. This is a common technique for solving a computational problem, writing it in terms of well-studied classes of computational problems with algorithms at hand. To evaluate an algorithm for its efficiency, we must learn how algorithmic efficiency is quantified. Analyzing algorithmic efficiency. For algorithm analysis to predict actual computer performance, it must be based on a realistic computer model. We adopt a common model called the random access machine, which has functionality similar to a single processor with basic instructions and data representations. The input to the algorithm is generally characterized by its size. The quantity that best represents an input size is often the number of pieces of basic data, such as the number of elements in a list. With a realistic model and characterization of inputs, the efficiency of an algorithm can be quantified in terms of the number of steps or operations that the model computer would take to solve a computational problem, called its runtime. Footnote here, it's important to note that the runtime of an algorithm is only correlated to the actual runtime of an instantiation of an algorithm. In a certain sense, characterizing an algorithm's efficiency is a matter of counting the number and execution time of each of its steps. Complications do arise, however. Analyzing the algorithmic efficiency of the EDD scheduling algorithm. As we saw in section 1.7.2, scheduling tasks with deadlines is a key aspect of real-time computing. An instantiated scheduling algorithm is called a scheduler, several of which have been developed for real-time systems. One of the simplest algorithms is Jackson's earliest due date algorithm. This algorithm minimizes the maximum lateness, the duration between a task's deadline and its completion, which is negative if it completes before its deadline. The algorithm can be described by Jackson's rule. Given a set of n independent tasks, any algorithm that executes the tasks in order of non-decreasing deadlines is optimal with respect to minimizing the maximum lateness. Setting up the scheduling problem. Consider such a set J of n independent tasks Ti, each with computation time Ci and deadline Di. Jackson's rule tells us that to minimize lateness, the tasks should be executed in deadline order, with tasks with shorter deadlines executed sooner. This amounts to the following computational problem. Input, an unordered list of n tasks. So T is a list of tasks, T1, T2 to Tn, each task having a computation time and a deadline. Output, a permutation of T, a list T prime, so T1 prime, T2 prime, etc., such that D1 prime is less than or equal to D2 prime less than or equal to Dn prime. We can see then that the scheduling problem has been cast as a sorting problem, perhaps the most well-studied class of computational problems for which there are many efficient algorithms. For concreteness, we will examine the efficiency of the insertion sort algorithm, which is one of many sorting algorithms available. The insertion sort algorithm, here is the pseudocode. The pseudocode describes the insertion sort algorithm. We have task insertion sort. We have the length of our task list, n, number of tasks. We have a for loop that starts at I equals 2 and goes to I equals n. So this for loop goes through each element starting at the second element. It selects out the ith element duration, so the duration of the ith element starting with 2, and it subtracts 1 from that to initialize j. If I was 2, j would be 1. Then we have a while loop. In this while loop, we are going to have the conditions that j be greater than 0 and dj, the duration of task j, be greater than the key duration. Okay, so while that is true, we do this. We shift the element in the jth position down, so j plus 1 would be down in the list, and then we step up with our j. So j minus 1 would be to step up our list with our index. We keep doing that where we shift down. Every time the duration of the task that we encounter is greater than the key, we're going to do this. We're going to shift that task down and effectively move our current task, the keyed task, up. Finally, this condition is no longer true, in which case we assign our keyed task to the new index for j and return t. We do that for loop all the way through, essentially shifting up our tasks to be in order. Let's take a look at an example visualizing the sorting process. A visualization of the sorting process on an example list of tasks is shown in the figure. So the input list is D1 through D10, so 10 elements in our list, and they start off unordered. 88 is the first one, 14, all the way down here to 73. So what this visualization shows us is how each element in the list moves at each outer loop iteration I, finally culminating in their final positions where we have a sorted list, which is what we wanted, a list with durations in increasing order, or non-decreasing order rather. So we have the initial positions. Then in the first step, we have a key of index 2, which is 14. We test to see, is 14 less than 88? It in fact is less than 88. So we move the 14 element up. We shift the D1 element, previously D1 element of 88, down. So we've rearranged these first two elements now to read 14 then 88. Our next step is going to swap 88 with 34. So 34 is our key duration. We'll swap it with 88. Good. We do that again with 62 and 88. So after 3 steps, we have the order 14, 34, 62, and then 88. Good. Now the key element is 90. However, 90 is greater than 88. So we won't swap on that iteration. Good. And we go to the next step, the 5th step, and our key is 16. When the key is 16, it is going to be less than 90. We're going to move up the list. See that it's less than 88. It's less than 62. It's less than 34. But it's greater than 14. So this is where it settles down to after the 5th iteration. So the inner loop, in this case, executed 4 times, whereas in the previous outer loop iterations, it had only operated once or 0 times. Good. That's how this proceeds all the way through the end of the list, and we have a sorted list once the outer loop has finished making it all the way down to the end of the list. Let's count executions. Analyzing the efficiency of the algorithm line by line, the number of executions of each line can be tabulated as shown at the right of the algorithm, repeated here. So we see our algorithm. On the right-hand side, we have the number of executions tabulated. Unless exempted by a conditional, each line inside the for loop will be executed at least n-1 times, and the loop conditions will be executed once more. So number of tasks, that'll get executed once, this one. Inside the for loop, we're going to get n-1 executions unless we have a while loop condition telling us not to execute that line. Executions of the lines of the while loop, so here's the inner while loop, depend on the ordering of the input list. And this varies with each I. So we assign variable mi to denote it. The minimum value for the while condition is n-1, which occurs when all mi equal 1, i.e. when the list is already in order. Okay. In general, the condition is executed sum from I equal 2 to n of mi times. So each line inside the loop is executed the sum of mi minus 1 times. Good. So we have these inner loop lines executed this number of times depending on mi each time. Counting executions. We take into account the fact that each line generally takes a different number of computational operations to execute. Each line should be weighted in the sum with the number of operations that it requires. We give line number k a weight ck that corresponds to its number of operations. Now we can sum this, giving the total number of operations n as n, big N of little n, equals C2, so the number of operations for line 2, plus C3 times n plus C4 times n minus 1. So these terms with n in them are the number of executions of each line, and the C terms are the number of operations for that line. As we have already seen, the number of while loop executions mi depends on the input list's orderedness. The best case scenario is when the list is already sorted, that is, mi equals 1. That would simplify our expression down to this expression. So in the best case, the total number of operations, n, is a linear function of the number of elements, n, in the list. We see that this is a linear function in n. In the worst case scenario, every potential while loop is executed, which occurs when the input is in reverse order. This reduces to a quadratic function of n instead of a linear function. Order of growth. The analysis of the task insertion sort algorithm in the previous section led to a best and worst case scenario, each of which was a function of n, the number of input tasks. These functions also depended on the number of operations per line, ck. When comparing the efficiency performance of the two algorithms, we frequently ignore these. Furthermore, we ignore the lower order terms in the function, which for large n typically have little impact. This leaves the fastest growing term of a function sans or without coefficient ck. For instance, the best case linear growth function would be characterized simply by n, and the worst case quadratic by n squared. It is typical to consider only the worst case when characterizing an algorithm, although this isn't always the case. Sometimes we're interested in the average. We would say that the task insertion sort algorithm is characterized by its worst case order of growth n squared. The convention for expressing this upper bound is O n squared in parentheses, called O notation or big O notation. In general, the pattern is O and then in parentheses is the fastest growing term without its coefficient. So that's the order of growth. Now, returning to the insertion sort example, the insertion sort algorithm is O n squared, which is common to several other sorting algorithms. So order n squared is common. There are some, like merge sort and heap sort, that are more efficient, order n log n, which grows slower than n squared. However, it is important not to lose sight of the fact that the worst case order of operations is not the only consideration. The average performance, low n application, and memory allocation may also be considered when determining the best sorting algorithm in a given situation. Some algorithms are more efficient for low n than they are for high n, so you might choose an algorithm based on the number of elements you're sorting. Okay, so that's algorithmic efficiency and order of growth. We'll see you next time.